Hello? Are you guys ready? Yes. All right, ready to go. That's good. Are you ready for the elections? No, that's right. Yeah. So I'm Ramesh, joint position between physics and engineering. I'm currently at LBL. So let me, on behalf of Steve, the department, welcome to everybody. Perhaps we should start with some great news. Marvin, congratulations. He just was announced the Franklin Medal. Incredibly prestigious award, so please join me in congratulating Marvin. And many more returns. So I'm on the colloquium committee, and so ComBio said, hey, why don't you introduce this in your zip code? I said, sure, no problems. I always try to make it very personal, so whatever comes from me is my own personal impressions. Now, Alex is someone that I always aspire to be. I'll tell you why. Alex is an amazing physicist, so there comes Steve. Do you have any words of wisdom? We started without you. Okay, thank you. Yeah. Sorry. Yeah. So when I was a student here, Alex had just come in from UCLA, and of course he was doing a lot of high TC, like all of us were doing high TC at that time. And it was just clear that he's incredibly creative. He's a guy who in the morning is doing condensed matter physics. In the evening, he's making an itty-bitty radio or making a device that works somewhere. And so he is, in Anderson's word, he is a true resonating valence point between applied stuff and fundamental physics. So I've always looked up to Alex and his research to see where he publishes, what he publishes. So it's a particular honor for me to introduce Alex. I will not go through his resume, which is 5 pages long, but I'll just tell you that he won the 2006 McGrody Prize, APS McGrody Prize, very prestigious. And it's supposed to be among the top 2 prizes in the APS, so it's a big deal. He has won 2 R&D 100 awards. That should tell you that he translates physics into a value proposition. So I won't take much time out of Alex's talk. He'll tell you a lot of fantastic things today. Alex.
Great, thank you, Ramesh. So here's the title of my talk. I'm going to concentrate on nanoscale physics and leapfrogging atoms and relativistic quantum craters. So that's quite a breadth. The materials I'm going to concentrate on are carbon nanotubes and graphene. And you see they have a very similar atomic structure. They're sp2 bonded carbon. And many, many talks have concentrated on the unusual electronic properties of these 2 materials. In fact, one was sort of discovered 25 years ago, the other isolated 10 years ago. And I'm not going to concentrate on those properties directly. I'll talk about using these materials to sort of enable devices or to actually study other kinds of physics that these materials allow you to access in an interesting way. So here's my outline. The first part, I'm going to talk about moving atoms, and I'll talk about deconstructionism. And this is not as negative as in philosophical discourse. It'll actually be kind of a positive thing. Then I'll talk about molecular scale integration, moving atoms again, and trying to image those directly with a transmission electron microscope. And then at the end, I'll talk about ultra-relativistic physics, atomic collapse, and something called quantum craters. So the first part, moving atoms part 1, I have 3 separate images here. The first is a can of Coke, second is a Doomsday Book, and the third is a moving car. So there's some connection between these 3. You probably cannot guess what that connection is, but I'll go through that. First is a can of Coke. There was the Department of Defense, and a few years ago, it awarded a very hefty research grant to Harvard University. And it was very specific. It said, here's the task we want you to do. We want you to take a can of Coke, put it on the tabletop, and we want that can of Coke sort of by itself to climb off the table, go onto the floor, scurry across the floor, and slip out the door, like this door, except the door is closed. The can of Coke had to slip under the door and reemerge on the other side of the door intact in its original size. So it couldn't tunnel through the door. The probability would be too small. It had to be some realistic thing. And so Harvard said, great, we'll take the money. And they set some graduate students to work doing this, and they drank a lot of cans of Coke. But they really didn't accomplish the task. It turned out to be pretty hard to do. So to do this, I've thought about this a little bit. What you really have to do is, the hard part is getting under the door. Scurrying across the floor is maybe hard, but not that difficult. But getting under that closed door where you just have a millimeter of space is kind of hard. So somehow you have to have some extreme shape shifting, or maybe deconstruct the can of Coke into its atomic constituents. The atoms slip under the door, and then the atoms reconstruct on the other side. That's one way to do it. So let's talk about this other topic. This is called the Doomsday Book. William the Conqueror commissioned this. It was sort of a survey or a census of the entire land, the holdings of England, and he basically wanted to know every person in the kingdom, every business. And the reason was to make sure those people pay taxes. And it was very complete. In fact, there's only one family that escaped being written down, and apparently that was Donald Trump's ancestors in Scotland. Okay, so this was commissioned in 1086 as the first complete survey of its kind in the world. And in 1986, 900 years later, the BBC in England decided to properly archive this book. It was written on vellum. You see, it's kind of, the pages are tearing off, they're yellowing, starting to crack, and so on. So they said, let's digitize this book with the state-of-the-art digital memory and archive it. And they used laser discs. They did this in 1986. 3 years later, the laser discs went bad, and they couldn't even read them anymore. So that kind of memory, or state-of-the-art, really wasn't even as good as the original book, which has lasted 900 years. So let's think about doing really archival memory. Is there a better way to do that? Somehow, maybe with solid state, atom deconstruction, reconstruction. Maybe we could have a system that has archival memory. The third one is this moving car. And the way I picture this car moving down the roadway is pretty much all the atoms are coupled together, and it just drives down the road. Pretty much all the atoms are lumped together and move bodily. Of course, there are complications. The pistons are going up and down, the wheels are turning, and so on. But for the most part, it's just one particle that's moving. And another way of maybe moving that car, which seems implausible, but worth thinking about, is maybe taking that car apart as it moves, or to get it to move. You sort of have the car just be stationary. You strip atoms off the bumper. You move them to the front end of the car and glue them onto the front bumper. So the car gets a little longer in the front, a little shorter in the back. And you keep doing that. You keep reconstructing the car in the front as you deconstruct it in the back. And that would move the car bodily down the roadway. That's not the way it happens, but maybe at the nanoscale that could happen. It'd be a way of transporting material from one place to the other. So let's look at these carbon nanotubes. This is a transmission electron micrograph of nanotubes. They're sort of these cylindrical objects, sort of the order of a nanometer or a few nanometers in diameter. They can be pretty long, microns, or even millimeters, or maybe even centimeters long. They come in these two forms, these single wall or multi-wall. This TEM image sort of does a cross section, so we can see the multiple walls, especially in the bottom image there. And you see there's a hollow space in here. So that's the space I'm interested in. And we can put things in there. We can synthesize these with stuff in there. And here's an example of an iron nanocrystal that is inside the hollow core of this nanotube. This is not a great image. It doesn't have super good resolution, but you see the nanocrystal. It has higher contrast. I sort of outlined where that hollow core is down the center. So what we're going to do is take that object, that nanotube, we're going to wire it up. We put electrodes at the end of it. Here's that nanocrystal, and we run a current through this circuit. And the interesting thing is that electrical current has a direct influence on the motion of that nanocrystal. It's not immediately obvious that that should happen, but let me show you a little video. And here's a real-time video. There's the nanocrystal. You see it's moving. It's moving to the left. And actually, we can make it move back again. We can move it back to the right. And we can move it back and forth by just reversing the electrical current. So somehow the electrical current through this nanotube is making this nanocrystal move. And we can stop it. We can make it move pretty fast. This is right at the threshold for moving it, so we can track it with the TEM. So now comes the question, well, why is this thing moving? How is it moving? And what happens when it hits a constriction? So here's another nanotube. Here's this nanocrystal. And this one actually has some defects in it, so it has a constriction. I've outlined the constriction there. So what I would expect is this nanocrystal gets here and then it gets jammed up. It's a solid nanocrystal, solid iron, and it just can't move anymore. So you could move it back again, but it can't get through that constriction. However, if you watch what really happens, that nanocrystal just squeezes right through that constriction, goes all the way through, it pops out on the other side and keeps going. And you might say, well, it's just, like rubber, it deforms. It does not deform. It's not molten. It's actually crystalline and solid and undistorted all the time, even when it goes through that constriction. And here's a diffraction. In the TEM, we can do diffraction on it. So it always remains solid and crystalline, and it squeezes through this constriction. So how could that possibly be? So Marvin Cohen and Steve Louie and their postdoc Sunisa Ko studied this problem. They came up with a pretty interesting model that says for this nanocrystal to squeeze through the constriction, you actually strip atoms off of the back, you transport them on the surface, kind of like a two-dimensional atom gas, and they reconstruct on the front end. And so you can grow this nanocrystal through any constriction you want, and it will reemerge on the other side, and it will always be crystalline. Just the surface atoms, these ones, are mobile on the surface. And you can compare how fast this thing is going as a function of how hard you're driving it or the voltage. The voltages are pretty small, just of the order of 1 volt. And you get very good agreement and can be pretty fast. You don't have that many atoms you're moving. Note that this atom B and atom C are completely stationary. All these atoms are stationary. In fact, most of the atoms are stationary while this thing's moving. Just the ones on the end are reconstructing on the front. And then after a while, atom C is at the end, and then it gets pushed to the front right there. So it's a new mechanism for transporting material. That's kind of interesting and seems to be observed in the TEM. Now what you can do is you can move this thing back and forth. You could say if it's on the left side of the tube or the right side, call that 0 and 1. So there's a logic states. And with the TEM, you can actually read out where it is. You can have a discrimination level. You could say, oh, that's a 0 or 1. But it turns out just with a blind resistance measurement, in other words, measure the electrical resistance between the ends of the nanotube, you can tell where that particle is, which is somewhat amazing. Basically, from classical physics, you don't really get that result. It's almost like the wave packet is going along through a ballistic conductor. It's reflecting off of that particle. It's like an interferometer a bit. And then from the interference, you can tell where that particle is. So we can read off blindly where the particle is. So we can write in these states. They're non-volatile. We can read them out multiple times. So we read it out, read it out. So reading it at low voltages does not disturb it, doesn't destroy the state. And so it's a memory device. It's pretty small. It's pretty robust. Some estimates are 1 terabit per inch squared, which is pretty high. Then Vin Crespi, a theorist at Penn State, has done some calculations to see how long this would last at room temperature, and he comes up with 10 to the 9th years, which is about the age of the universe, almost the age of the universe. So that's a long time. The thing is hermetically sealed, doesn't oxidize. It's an interesting device. I'm not saying this is going to be the next memory device, but it's something to think about. It's sort of an electromechanical system that is very small, very robust, and high density. Let me move on to sort of a higher order device, which is a radio. Radio technology has been around for over 100 years. Sort of started with Marconi and others in putting together radio transmitters and receivers. And these things are pretty crude. They didn't have the bandwidth to do voice communication. That's why you used Morse code. They worked pretty well. And then this got revolutionized sort of in the 1920s when people invented vacuum tubes. And with these vacuum tubes, you could make the material, the whole system smaller. and had pretty high bandwidth, so you could have voice communication and so on. And another revolution happened when the transistor, solid-state transistor, was invented. Then you could have very small, low-power devices you could just hold in your hand and listen to the radio. And then again, integrated circuitry allowed all these interesting devices we're using today, like smartphones and so on. So the key developments were theory, electromagnetic theory from Maxwell's time and so on, and quantum mechanics in helping you understand and fabricate transistors, and then the materials like silicon, understanding semiconductor physics, and then integration was key to this too. In fact, a Nobel Prize was not too long ago awarded for integration for these integrated circuits. So if I want to make this really small, okay, your iPhone already has pretty small circuitry, but it's not molecular scale, it's huge on that scale, so I'd like to make this radio at a molecular scale. How would I do that? Well, I have to understand the basics of a radio receiver. So from a physicist's point of view, this is what I think of a radio. I have an antenna, a tuner, amplifier, demodulator. Those are the basic parts of a radio, and then I convert that through some transducer to a speaker. I can then hear what's going on. So this is the basic circuit diagram for a radio. There are other simpler circuit diagrams for things that are supposedly smart, and here's one, the Samsung Galaxy Note 7. That's the circuit diagram for that thing. Okay, so let's get back to a radio receiver. The thing that bothers me the most about this whole block diagram is the tuner. That sounds complicated. It's something that has to have a resonance here at a certain frequency. You want to have a fairly high Q. And the way to do that, you know, the way you learn in physics 7B or something, is just use an LRC circuit. An inductor, resistor, capacitor, just put that together. So let's try making an LRC circuit at the nanoscale. Capacitors and resistors are pretty easy to make. Just some wire, there's a resistor, two wires near each other, there's a capacitor. But this inductor, this coil, that's tricky. People have tried to make small inductors. Here's a pretty nice one. It's from a few years ago. And it's not really that small. Here's 50 microns, so human hair will just barely fit in that thing. So as far as I'm concerned, that's huge. And then when you measure the electronic properties of that, it has a Q of 15, which is state of the art for this kind of circuit. And it's just terrible. That's not going to work. So these electronic circuits just don't seem to be that good. It's hard to do this at a really small scale. So let's go, you know, sort of change course a little bit and try mechanical oscillations. If you're trying to make something small and you're working with electronics, and electronics are pretty sophisticated, it seems ridiculous to go to mechanical. It seems like a complicated thing to do. But let's just look at it. Here's a little girl. She's jumping off a diving board. And that diving board resonates at around 1 hertz. And it's sort of the order of 1 meter. And then you start banging on a xylophone. You have smaller plates that vibrate, and the frequencies are higher, sort of in the audio range. And you can make this even smaller. This is a few microns, and you have this little thing that looks like a harp, and you twang these things, and they're in the megahertz range. So presumably, if you went even smaller, you could get all the way to the gigahertz range. So there's a fantastic frequency range for mechanical oscillators. And these things have been called micro-electromechanical systems or nano-electromechanical systems. So it's not unreasonable to try to do this. So I want to try to make a tuner, a tunable oscillator that's mechanical, that might be, you know, for my radio, the heart of it. So here's a video. This was actually put together by an undergrad here at Berkeley. And so this is trying to use 2 nanotubes to try to make a tunable oscillator. So it's a double wall tube. We're just racing down the center between those. And somehow you fuse another nanotube to this. And then you pull this out and sort of telescope these 2 tubes. And then you have some radio frequency drive this thing, and it starts oscillating. And then you make it shorter, it oscillates faster. So if you change the length of it, you have a tunable oscillator, an electromechanical oscillator. So it sounds a little complicated, but at least it works. At least in this simulation, it works. And then we did it. We made this thing, and it's actually very challenging to make this. We had to design and build a nano manipulator that fit inside the transmission electron microscope, so we could do these manipulations of fusing things together, pulling them and driving them and oscillating them. But it works pretty well. So here's the nanotube. You see it's telescoped out, it has a certain length. And then it vibrates. This resonates at 225 megahertz, just about right, or in the right ballpark for commercial radio transmission. And we make it a little bit longer, pull this out a little bit more. the frequency has gone down, it's completely tunable. So then we worked with the other components of this. This is the tuner I just talked about. An antenna seems easy. You just take a wire. The impedance matching might be a problem. Then the amplifier, we learned how to make field effect transistors with nanotubes, and they work pretty well. They're fairly small. And then this diode, this demodulator, Marvin Cohen and Stephen Louie actually predicted that if you take one nanotube and fuse it to another with this 5-7 defect, which replaces some of the hexagons, you could have a metal to semiconductor interface that's very small, and this becomes a Schottky barrier that has rectifying behavior. And we made that, and it worked. That's actually an experimental result from this single nanotube device. That's a rectifier. And so now we just had to put those things together to make a small radio. The problem is these are sort of discrete elements, and we thought about putting them on a silicon chip and the whole bit. And the more we thought about this, the more we ran into problems, and we realized this integration was really troublesome, and we were thinking like an Intel engineer or something, and it just wasn't going to work. It was an integration nightmare, so we completely threw all this stuff out. Said that's not going to work. We need a better approach, sort of a out-of-the-box approach to integrating this together, and it became clear that we really should be doing more than just putting these discrete elements on a chip and trying to tie them together with wires or something. We should be integrating the functions together on a single molecular structure. So we went simpler instead of more complicated. So here was our plan. We're going to take a nanotube. This is the nanotube schematically. We're going to connect it up to a wire. Here's a battery, and here's an electrode, and that's the entire radio receiver. It's a lot simpler. It's easier to make that thing, too. So it's an all-in-one nanotube radio. And I claim all these functions that are highlighted in yellow here are built into this. I showed this to some electrical engineers, and they said, "You're crazy. That doesn't work at all. Don't you know anything about radios?" And I said, well, let's actually go through this. So let me quickly go through the functions, how this thing will actually work. The first thing is you need an antenna. This is not an electronic antenna. This is a mechanical antenna. So you've got this cantilevered beam here. It's clamped only in one place. It's not this telescoped, sliding trombone-like beam. It's just one. It gets charged. In fact, most of the charge accumulates on the tip. And then this wave comes along, this radio transmission wave. And if this thing has electric fields that are polarized here, this thing will start oscillating. So it's an antenna. It's a mechanical antenna. It'll start moving, being driven by the radio transmitted wave. In fact, in your inner ear, there are things that look very much like this, cilia, and they move in response to the sound wave, mechanical sound wave, and that's how you have transduction from a sound wave to electrical pulses inside your ear. It's very similar geometry, in fact. Same kind of mechanical antenna. So the tuner, well, the tuner is the antenna, right? This only starts vibrating like crazy when this frequency matches this frequency, and other frequencies, it just kind of sits there. So it works. It filters all the other frequencies out, and it resonates at this magic frequency, the carrier wave frequency right there. Amplification. How do we get an amplifier out of this? Well, we put on a big enough voltage so you get field emission. So the electrons tunnel off of this tip and tunnel over here. Field emission currents. That's like an old-fashioned vacuum tube. Old vacuum tubes were pretty good amplifiers. They didn't use solid-state transistors, so this is kind of like a small vacuum tube and works as an amplifier. Demodulation. Okay, somehow the nonlinearities of this process and tunneling across here gives you demodulation. And let me show you how that works. So we tunnel into the vacuum, through the vacuum of this. So we've got a nanotube. We're tunneling through this barrier. We can adjust that barrier with electric field. In fact, Fowler and Nordheim worked this out shortly after quantum mechanics was invented in the 1920s. They came up with this expression for the emission current. And there is this field enhancement factor in here that has to do with the radius of the tip and the electric field and so on. And that field enhancement factor depends on the position of the oscillating tube. And so you put that into this, you put this, this field enhancement factor into this equation, which is now modulated because it's oscillating up and down. And that gives you a demodulation. You expand this term, and it's basically a square wave detector, a square law detector. So it demodulates. This automatically gives it for you. And so you have everything, and all you have to do is put an ammeter here, and it's already demodulated current that goes through that ammeter. And that's your audio signal that's decoded from the transmitted RF carrier that's been AM or FM coded. The sensitivity we can calculate. It's like a simple harmonic oscillator. We put temperature in as well, and so obviously lower temperatures give you a lower detection limit, so it works better at low temperatures, but we'd like it to operate at room temperature, obviously. So we're pretty much there, but I haven't talked about tuning yet, how you get different radio stations from this. That has to be built in as well. And so here's a character that liked to change notes, change frequency. You guys know who this is? Yeah. Who's that? Jimi Hendrix, that's right. I showed this one time and somebody said, that's Prince. I go, oh, come on. Prince, that's Jimi Hendrix, okay, the greatest guitar player of all time. Jimi Hendrix loved to play different notes, change frequency. This is how Jimi Hendrix does it. Okay, if you want to get a higher frequency, you just shorten that string, right? So the way we get this into the right frequency band is we actually put a huge field emission current on this temporarily, so strong that it boils atoms off the end and just burns the nanotube shorter and shorter until it's in the right band. So it could be, 500 megahertz or around 100 megahertz or kilohertz, whatever we want. We stop it then, and then you see this is shorter than this one. And so this is, of course, non-reversible. But you stop it, and then it's frozen in. You have now generated the right band for your radio to operate. So now how do you do fine-tuning? How do you tune in different radio stations once you've made that radio? Well, then you just play with the tension. It's like doing fine-tuning here. Changing the tension in that string changes the fundamental frequency. And we have access to an electric field here between this tip and this plate. And that electric field tensions this a little bit. And the more voltage we put on, the more it tensions it. And we can reversibly sweep through the different frequencies. You see, this is a few hundred megahertz, and we can easily go down to 100 megahertz or so into the commercial radio band region. So here's actually this radio you can watch operate, unlike most solid-state radios. And here this thing is off resonance. Here there's a transmission that's matching that frequency. The thing vibrates back and forth, and it gets kind of fuzzy. Let me see if I can play you a little actual video of this thing operating. And so you could hear that, that was pretty good. You probably recognize that song, or you should. And that it did everything. We could tune in, we could demodulate. That was an FM transmission, and it's all built in there. This is very sensitive. Some people say, well, that's kind of scratchy. My MP3 player is better. And I say, well, come on, this is a single molecule doing all this stuff. And in fact, that scratchiness it's operated in a vacuum. It's not a perfect vacuum. Once in a while, atoms land on the tip. They change the field emission. We don't have a great vacuum. It's kind of a crude vacuum. And you're sort of hearing atoms landing on this thing. That's why it was a little scratchy. We could filter that out if we wanted to. There was no processing to that at all. I was just straight listening to the current coming out. Absolutely no filter. So the thing is, if you can sort of pick up frequency shifts by atoms landing on there, could you use this as a nanomechanical balance? Could you weigh atoms with it? There's a holy grail of nanomechanical systems. Could you weigh a single molecule at low temperatures? Or could you even weigh a single atom? And it would be even better if you could do it at room temperature, where you have more thermal noise. So here's the idea. This little girl, once she jumps off the diving board's going to oscillate a little faster once she leaves it. So when she's on there, it has a certain frequency. When she jumps off, the frequency is a little higher. From that frequency shift, you could determine her mass, knowing properties of the diving board. So people were thinking about this. There's some other folks, and they put some little beads onto a little nano cantilever or micro cantilever. But this is huge. I mean, they're thousands, if not millions of atoms in that little bead. I'm talking about a single molecule or a single atom even. But we're going to use this radio. because the radio actually is sensitive enough to do that. So we don't really have to change the geometry. And when we do that, we throw some gold atoms on there and the frequency shifts. And when we do the analysis, we can actually measure half a gold atom per root hertz at room temperature. So this is the first nanomechanical balance that has atomic resolution at room temperature. It's really a fantastic achievement for NEM systems. Here's another interesting thing. In electronics, actually because the electron has a discrete charge, its charge is quantized, if you run a current through something, the electrons will come out in bunches. The electrical current is quantized. So in vacuum tubes or even in semiconductor devices, these electrons hitting the end contact will give you a noise distribution called shot noise. And from shot noise, you can actually determine the charge on the electron. So what about our system? There are atoms coming, they're sort of one by one hitting our oscillator. We should get a noise spectrum for the frequency shifts. And from that, we should be able to determine sort of independently the mass of the atom hitting this thing. So is there atomic mass shot noise? Has anybody ever seen that? To my knowledge, nobody had ever seen that. And in fact, we used that. We got the right frequency distribution for the noise spectrum, and we got the right mass out of this. In fact, we got 0.29 zeptograms, and the correct mass for gold using well-established techniques is within our error, 0.327 zeptograms. So the message is we can use this sort of independently to measure mass, and shot noise for atomic mass has been observed. Let me move on to actually seeing atoms and seeing atoms move directly. And I'm going to concentrate on this transmission electron microscopy, which has become a very powerful tool. If you think about a conventional light microscope, you're limited by the diffraction. And basically, the resolution is roughly the wavelength. And the wavelength is, of course, given by Planck's constant divided by the momentum. So for photons with visible light, you have a resolution, roughly in this range, or it can be a little bit better, about 1,500 angstroms. So if you have interatomic distances of, say, 1 angstrom, you can never use an optical microscope to see those atoms. It just won't work. Now, there are tricks, maybe having some atoms or some molecules light up at different times. And that's, a new process in biological imaging using visible light and so on. But to see a uniform system and see the atoms with an optical microscope will not work. Now, what about a transmission electron microscope? The thing is, you can use electrons instead of visible light. You can have them at pretty high energy, and then the wavelength becomes very small, 0.04 angstroms. This is a typical transmission electron microscope energy. And so in principle, it would have a resolution of 0.04 angstroms, which is way better than you need to see atoms near each other. In fact, this is the original TEM developed by Ernst Ruska. And Ernst made this, he started working on this in 1930. By 1933, he was already beating the best optical microscopes. And by 1934, 35, he had a lot of operating machines that were really quite good. The Nobel Prize Committee immediately recognized how important this was. And a mere 56 years later, he won the Nobel Prize for that discovery, or that invention. So let's forget about this thing. Let's use this transmission electron microscope and look and see if we can see atoms and see them do interesting things. So we're going to look at graphene. This is the crystal structure of graphite. We'll just peel off one of these layers, and the bond length in plane is about 1.42 angstroms. These van der Waals distances are bigger, but that's what we're going to cleave. So we're going to be interested in these distances here, about 1.4 angstroms. So we need resolution better than that to see those atoms. So we were actually the first group to suspend monolayer graphene and put it in the TEM and look at it. And with my TEM, which is in the basement of Burge Hall, we looked at this, and this picture depends on your point of view. Either it's beautiful or it's totally worthless. I don't see anything here whatsoever. Okay, there's some electronic noise. So that means it's clean. You're not seeing a bunch of garbage on there. But unfortunately, our microscope only has 2 angstrom resolution, and we need 1.4. So we're just a little bit beyond that, and we cannot see anything. The problem with my microscope and most microscopes like it is it does have aberrations. It's got, just like optical microscopes, some spherical aberration. Of course, they're magnetic lenses, not optical lenses, but similar problems. It's It's got chromatic aberrations as well. And so that makes the resolution only 2 angstroms, even though the wavelength of the particles, the electrons, is much smaller than that. It doesn't matter. There are other problems that dominate. So the Department of Energy appreciated this problem. And so a little over a decade ago, they put a huge effort into building a next generation of transmission electron microscopes that have these aberrations corrected. And LBL was the lead institution that drove this project, and it's called the Transmission Electron Aberration Corrected Microscope 0.5, and that 0.5 was, they were targeting a resolution of 0.5 angstroms. Very, very ambitious, and they put a lot of money into this. It could operate at reasonably low energies, which is another good thing, because high energy electrons tear up samples like graphene. And so when this machine was finally built, not too long ago, we took our graphene, which we had suspended, we put it in that machine, and that's what we got. And so it just jumps out at you. You know, you see the hexagon. There's one atom, another carbon atom, another one, another one. They're the 6-fold rings. And this is perfect, has absolutely no defects in it. And, you know, from seeing absolutely nothing to seeing like something like this, it was really pretty spectacular. But you look at this for a while, and then you get bored with it, you know. Maybe you look at it for a few days, and then, but believe me, after a week or so, you get bored. And so you look for other things. And it had been predicted that if you grow graphene, say with chemical vapor deposition, you're going to get domains. And this is an example of a sort of a domain wall where we have one domain here. You see these angles of these bonds are shifted with respect to these. So there's a grain here, another grain, or a single crystal region here and here, but they're separated. And the theorists had predicted that these 5-7 defects, 7-fold, 5-fold, 7-fold, these pairs would minimize the strain energy between these domains. If you try to do this with just hexagons, it's just way too much energy. It's way too costly. So we wanted to see, is that really what happens, or are they just making stuff up? You know, could we see this with our microscope? And so this is with that team microscope looking at a domain boundary, and all we've done here is colored in these 7s and 5s. Everything else is hexagons, and you see perfectly this serpentine path of 5-7s. Here's another grain boundary again. So indeed, the theorists were right, and we could see this directly. And we did things like we tore the graphene to see if these domain walls were weaker than the regular graphene. We studied electrical properties and so on. So it's pretty nice to be able to see all this stuff in situ. Then we got bored again and said, well, this is all kind of static. Let's see if we can do something dynamic. So what we did is we punched a hole in the graphene. Intentionally, we focused the electron beam, made it so intense that it knocked out some carbon. And these colors are just for fun. And here's the hole. We punched in here. Whenever you see a scanning tunneling microscope image, it's always colored like this. And I used to do a lot of STM work, so I couldn't help myself. This is probably the only TEM image that's ever been colored, but makes it look nice. So let me show you a video of this, because we could look at this basically in real time. This has been sped up a little bit. This is actual data from the TEM. And this is that hole we punched. And you can see the edges. These are individual carbon atoms right here. And I'm going to run this thing, and we're constantly bombarding it with 80 keV electrons. So the edge is kind of hot. It's nominally at room temperature, but we're throwing electrons in. They're kind of heating up the edge. And we're hoping to knock off some atoms and see the dynamics. We're hoping to see atoms move sort of in real time. Let me play the video. You can watch this. This was done a few years ago, but it was the first video ever taken of carbon atoms moving. And I'm still impressed each time I see this, because you can just see sort of metastable states where this locks in at the edge. You see hexagons form, disappear. And you know, for somebody who grew up, and when I looked in a chemistry book and I just saw styrofoam balls stuck together with toothpicks, and they said that's what atoms are, and now you actually see them moving around basically in real time. That's quite amazing. In fact, if you look at the edge, here's one image. You've got 2 atoms forming a complete hexagon. Here are 2 missing atoms, and 4 seconds later, these atoms had leapfrogged over and joined here. So they're kind of mobile on the surface. Overall, we're knocking some out, but there's some interesting dynamics going on. And again, we teamed up with Marvin Cohen and Stephen Louie and their students and postdocs who did some molecular dynamics simulations of this. And they got some really nice agreements. Of course, this isn't the perfect one-to-one because it's sort of a random process, but you get these edges, these are called armchair edges. It looks kind of like an armchair, I guess, part of it. And this is called zigzag. It zigzags back and forth. And we get a lot of these zigzag edges and armchairs. And that's exactly what came out of these simulations, putting in the right potentials, and also effectively heating up the edge to drive off the atoms. So those are sort of interesting quasi-stable states. Some other theorists had made some interesting predictions, though. And here's one of these zigzag edges, and they said, you know, that zigzag edge is not completely stable. It can reconstruct. Here's the zigzag edge again, but the edge atoms can reconstruct, and it's called zigzag 5-7 because you have now, instead of hexagons, you've got a heptagon, pentagon, 5-7 reformation at the edge. In fact, that is lower energy than the original zigzag. So the idea was maybe it drops to this low energy state and stays there. And so pictures like this, which I showed before, may be total nonsense. And a lot of theorists had calculated electronic properties for ribbons that look like this, and this has a zigzag edge. Here's a zigzag edge. That may be completely unstable. You'd never get that, even forgetting about hydrogenation and interactions with substrates and so on. So we wanted to see, is that really stable? Can you ever really get that edge at room temperature? So what we did is we prepared a very clean edge. Here's a beautiful zigzag edge. A little bit time earlier, you see this perfect 5-7 reconstruction. Then it switches here, it switches back, it switches. So the electron beam is actually kicking it between these two metastable states. It's a little bit higher energy here, but metastable, and it jumps back down again, it jumps back and forth. And if you blank the beam, it'll freeze in this state. This state is metastable enough, has a high enough activation barrier, so at room temperature, it'll freeze in. In fact, Sinisa Ko, who is Marvin Cohen and Steve Louie's postdoc, calculated how this thing zips along and the time scales and got the activation energies and so on, and actually extracted a lot of information from that. So we were able to, sort of in real time, see these dynamic processes. Let me turn to using graphene in a TEM in a slightly different way. Right here, I have a fish sitting in a net. Okay, now this net happens to be like graphene. And so the question is, can I sort of do this in the TEM? And let's say I'm interested in the dynamics of that fish, and I really don't want it to be attached to the net so strongly. So the fish is sort of flopping around doing its stuff. And I want to study the fish, and I don't care about the graphene. So let me concentrate on this. So in other words, we're going to use the graphene as a support structure and have molecules sitting on it. And we hope it isn't perturbed too much by the graphene, and it allows the electrons to transmit through. And this is a contact here, carbon contact, another carbon contact. This is graphene, which you don't care about. And this is a single alkane chain molecule between these. And now we can watch it move. This is now moving at room temperature. So you see a single molecule there suspended between these two contacts. It's floating above the graphene. And you see there's some entropic effects. It's kinking up, moving around. You see it kink there, stretches out again, kinks up again, does its stuff. In principle, you could be measuring electrical conductivity through it at the same time, and some theorists here at Berkeley are studying that, but here you could watch that in real time. So this graphene gives you an advantage in the TEM. But what if, going back to that fish is going to die pretty quickly if it's out of water. What if you wanted to have these creatures in their native environment? Okay, you want to have a fish in water instead. You have something like a little aquarium, so you need transparent windows and a liquid in there. And the TEM is a high vacuum environment, so you don't really want to put a droplet of water in there. It's going to mess the whole thing up. So we came up with this idea of using graphene as a liquid cell. Sort of you have a little liquid blister, and you have one layer of graphene on the top, another layer of graphene on the bottom, and you encapsulate this liquid, which has your atomic species where you can do chemical reactions and watch chemical reactions in real time with atomic resolution in the TEM. So sort of watching chemical reactions happen. You can even drive them with the electron beam, stimulate them, or you can heat this thing up, and so on. So this is what we called our graphene liquid cell. We teamed up with Paul Alvasados in the chemistry department here, who'd been studying nanocrystals for a long time. And so we're trying to grow nanocrystals, and we grew platinum nanocrystals, for example, in a liquid environment, and the electron beam stimulated the growth. And we could watch exactly where the atoms attached. We could have two different particles come together, fuse together. We could see where the active sites were. We could see if there was a grain boundary in the middle of these things after they merged, and so on and so forth. So we could really study nanocrystal growth at the atomic scale with atomic resolution virtually in real time. And so there are many other things you can do with this. You can do biology experiments. If you put DNA in here, it turns out that graphene actually protects the DNA. And so the electron beam, even though it's pretty powerful, it doesn't destroy the biological species as quickly as you might guess. Silicon nitride windows aren't very good, so graphene really has additional benefits other than just letting the electrons through and containing the liquid. So let me change gears a little bit here, and from going with the transmission electron microscope, I'm going to now switch to a different kind of microscope, and we're going to use a scanning tunneling microscope. And the thing we want to study seems very far from this kind of graphene or nanotube or solid-state physics, and it has to do with atomic physics. It's something called atomic collapse. Let me explain what atomic collapse is. If you go back to your elementary quantum mechanics course, like 137A, you study sort of the Bohr model, and you have a nucleus, you have an electron, and you get these solutions to the Schrodinger equation. And you get these bound states, basically the orbitals. And that happens, you get these bound states for all nuclear charges Z. It really doesn't matter, there's no cutoff, Z is arbitrary. Get bound states for all Z. That's the non-relativistic solution. Okay. Now it turns out, if you go to the ultra-relativistic case, that model breaks down. And you have a critical nuclear charge. And if you're below that charge, Z is less than Z critical, the electron doesn't have a bound state. It just basically bounces off. It's going so fast, it doesn't form a bound state with that nucleus. So what you do is you just crank up Z here to make this stronger and stronger and stronger, more protons in there. You get above some critical charge, and then the electron actually spirals in to the nucleus. Okay. So it's different from this case as well. And that's called atomic collapse. When you get so strong, this thing just spirals in. So two Russian theorists, actually in 1945, 70 years ago, studied this and made a prediction. And it's a little more complicated, but a back-of-the-envelope type calculation says that this critical charge Z is basically 1 over the fine structure constant. All right, if you guys are taking physics 137, you know where 137 comes from. It's just the inverse of fine structure constant. It's got the speed of light built into it here. Okay? Now, nobody has ever seen this. They've looked for it, but nobody's ever seen this atomic collapse. This is a pretty heavy nucleus. Actually, if you do this correctly, you get a number like 160 or something. And so if you wanted to see this, I guess you'd have to have some big accelerator. You'd make some very heavy nucleus. That nucleus would tear an electron out of the vacuum, and you'd get positron emission. So you'd look for positron emission to see if you have this interesting state. Nobody's ever seen that. So I'm not an accelerator person, so I'm not going to do this. But we teamed up with Mike Cromie, and Mike Cromie is an STM expert. And the suggestion was to actually build an artificial nucleus by hand in the STM. And Mike has a lot of experience moving atoms around on surfaces with the STM. With the TEM, you can't really do that. We have nanomanipulators, but it's very difficult to move individual atoms where we want them. But the STM, that has been refined. So Mike was an expert at this. And so the idea is you build this on top of graphene. So I show this sort of as a sheet of single layer graphene. We're going to build this nucleus on the graphene by taking some nuclear charges. And the key to this is the effective fine structure constant, which has the speed of light. That C, that's here in the denominator, is replaced by the Fermi velocity, so you gain a couple of orders of magnitude there. So the effective alpha is 2 orders of magnitude different. And so the Z, from going from 137 or 160, somewhere around there, it goes to 1. So you just need 1 proton charge to do that if you build this artificial nucleus on graphene. So Stephen Louis and his team did some calculations of what the charge transfer would be if you used calcium dimers. Those are things Mike can actually move around with his STM at low temperatures. And the calculation said, well, if you have 1 calcium dimer, you actually are sort of halfway there to criticality. You just need 2 dimers, and you're already at this atomic collapse threshold. So Yang Wang and Dylan Wong, students in Mike's lab, did this. They were just pushing calcium dimers together. Here's one dimer. It looks like a circle, but it's actually a dimer. Here are two dimers, 3, 4, and 5. And then they did spectroscopy nearby to see if anything unusual happened. And this is a known feature in the spectrum called the Dirac point for graphene. But then they saw this new resonance right here. It already shows up a little bit at n equals 2. Don't have it here. So this is right where threshold is. And then you have this very strong resonance. And so some theorists at MIT, headed by Levitov, did some calculations. And for this atomic collapse state, these are their predictions. And these sort of match vertically. N equals 1, 1 dimer, 3 dimers, 5. And you get very good agreement where this is the atomic collapse state. That matches quite nicely. In fact, you can look at how this drops off as a function of position. This is sort of psi squared for this resonance, if you will. And the theory and experiment match pretty well. And so you can say atomic collapse has been observed in graphene, in this pseudo very heavy nucleus. So we're looking at interesting physics and using graphene as a mechanism to explore that physics without having to go to accelerators. So it's kind of a nice application to solid state system. Now something else we can do that's pretty interesting is we've learned that with the STM and having boron nitride underneath, and that previous image or the previous study actually had boron nitride in it as well, and we had to take the dielectric response into account and so on. That enables you to, with the STM, pulse and make regions of N-doped and then P-doped for the graphene. So we can dope graphene where we want and make potential wells or make PN junctions or just write little circuits of P-type material and have it separated by N-type material or vice versa. So that's a big plus. And you can see this region, if you had electrons confined in here, this sort of forms a potential well for them. And this is hole-like states out here, electron-like states. So looking at this simple particle in a box type picture, of course, this is a circular well. You might get some sort of Bessel functions in there. And this is what you'd have for the electron-like states. But this is very different from regular electrons because these electrons in graphene behave like massless Dirac fermions. They actually have a linear dispersion relation, so they're very different from regular electrons, say, in copper. They look like they're relativistic particles that have a linear dispersion, so the speed of light sort of is equivalent to the Fermi velocity in here. So we have this interesting confinement. There's some unusual tunneling that might take place at these boundaries because of that. And so what Mike's students did is they went into this region and just did spectroscopy, and they got pictures like this. Okay, so this is now looking at these relativistic things. We call them quantum craters instead of quantum corrals. Mike Cromie became famous 20 years ago when he and Don Eigler did this quantum corral where they put a barrier, circular barrier, on metals and looked at the regular electrons scattering around in there and imaged that. This is now very different. This is looking at the massless Dirac fermions or the relativistic analog of that. So it again is looking at different physics with this graphene. I think it's really a beautiful example of using this material to enable other kinds of studies. So I'm going to end there. I'm going to acknowledge these institutions that helped fund this research, but even more important are the people. I've already mentioned some of these, the faculty and senior scientists who helped contribute here, graduate students and postdocs from my group and from the other relevant groups. But the thing I want to emphasize probably the most here is that these are undergraduates. And this is a list of undergraduates that right now are doing research in my group. You see there are quite a few of them. These are people who are volunteers. They're very excited about physics research. And without them, this would be impossible. This research we're doing would be impossible because we need that additional power and the insight. And having these really bright undergraduates participate, I think, is fantastic. OK, so thanks for your attention.
Condensed matter physics and radios. Questions from the audience? Yes, sir.
I'm curious about your iron nanotubes. of impurities in that iron. Like carbon, for example, as a tail is. Do you watch that migrate also, or does it stay where it is?
That's a great question. In principle, we've talked about that. We'd like to put alloys in and see if they remain the same, or if you have that impurity, does it end up in the front or the back? The kinds of experiments I was showing you, were the resolution wasn't good enough to do that with that microscope. With the team microscope, in principle, you can do it. It actually is kind of hard to put wires in and do that in situ stuff with the other microscope. But that's a great experiment. We've talked about it. We haven't actually done that. Yeah, the electrons are called, massless Dirac fermions, and you say they're relativistic. They are not actually moving at the speed of light or close to the speed of light. They're moving at a standard Fermi velocity, which is 2 orders of magnitude less, but they have a dispersion relation, meaning energy versus momentum, that is not electron-like, not free electron-like, and that would be energy goes as momentum squared. It goes linearly with momentum, which is the dispersion relation for photons. So they're sort of, regular electrons, but they are behaving as if they were relativistic particles having that photon dispersion relation. And that's the connection. Well, we were just interested in, trying to make the physics all work, and all kinds of applications come to mind. I got calls from people like doctors who said they want to have little, radios go through the body and transmit information out. It's kind of hard to actually get information transmitted out with optical means or so on, but radio frequency works pretty well. So they were looking at that. I got calls from the CIA who said they wanted to use this stuff. I told them to go away. Anyway, anything, I think it was just to show that we could integrate something together and have it have that many functions in a single molecular device. That was for us the challenge, and having rather sophisticated functions all work together. You can think of applications too where you just need ultra lightweight things, but I think it shows that NEMS really at that scale, it can still function, and it's not an impossible hurdle to integrate things together. It's really kind of a new paradigm, very much like taking a bunch of transistors that were soldered together and then doing integrated circuitry. It's a new way of integrating things together. Multi-functions in one molecular device. That's really what you have to do.
Any other questions for Alex? If not, please join me.
Okay, thanks.